All right, so this is actually a test that I gave last year, which if you're keeping score would have been 2019. By the time you watch this video, it might not be last year anymore. It might be 10 years ago. I don't know. Hopefully not. So here we go. It says Sally stands at the top of a cliff that's 30 meters tall and drops a ball off the edge. At the exact same instant, Roy launches a ball straight up into the air from the bottom of the cliff at 18 meters a second. So we got to figure out, in part A, we got to figure out how far below the top of the cliff the two balls are when they cross paths, and then B asks us to draw the position time graph that represents the motion of the balls. All right? So sooner or later, we're going to need to make a position time graph. So I feel like doing that means that we should probably start by trying to write out an expression that describes the position of Sally's ball at time t and the position of Roy's ball at time t. Okay? So let's go over here to the side and make ourselves a little drawing. So, right? So, oops. Okay, so here's Sally. Oops. I was trying to draw her purple and it didn't take. There we go. So here's Sally. Hello. So let's see. So what happens? She drops a ball off the edge. So VI is 0, and it's going to fall a distance of 30 meters. All right. Meanwhile, we've also got Roy down here. Oops, that's not what I wanted to do. Meanwhile, we've also got Roy down here. He's going to throw his ball up into the air, and it will presumably come back down. He throws it up with an initial velocity of 18 meters per second. Oh, I used VI twice. That is terrible. So this is the initial velocity for Roy's ball, and this is the initial velocity for Sally's ball. All right, and so the question wants to know at what time they have the same position. So to solve this, I guess we need to figure out how we want to set up our position line, right? So I think what probably makes the most sense to me is to draw a number line that goes this way, and let's call this x equals 0, which means up here we're at x equals, 30, because that's how tall the cliff is, right? Okay? So, people's knee-jerk reaction is to think in terms of displacement, right? Because in honors, we use this equation all the time, right? But the problem is, because they're not starting in the same position, when they cross, they don't have the same displacement, right? Like maybe they cross when the purple ball has gone down 20 meters, which would mean that the red ball is only 10 meters up, right? Plus the fact that the signs are different, that definitely complicates things a little bit. All right? So when we did problems like this earlier this term, what I told you was, I think it's the second equation on the new honors physics or AP physics sheet says this: position at time t is, and it's something along the lines of right? And basically what they've done is they've just subtracted initial position, or added initial position to both sides of this equation, right? Because remember, delta x is just your position minus your initial position. Okay? So, what I'm going to do then is I'm going to use this equation to express the position of both Sally's ball and Roy's ball. All right, so let's do Sally first. So the position of Sally's ball is 1/2. Let's see, the acceleration is negative 9.8. You can use negative 10 if you want. Times t. The time is always changing, so that's t. Plus the initial velocity. Oh, that's 0. Plus the starting position. Well, Sally's ball has a starting position of 30, right? Okay, so if I simplify this, I'm going to find that the position of Sally's ball is negative 4.9 t squared plus 30. Okay, now let's repeat that same process for Roy's ball. Okay, so the position for Roy's ball is 1/2 times the acceleration times t squared plus the initial velocity. Oh, that was 18 times t, plus that had an initial position of 0. So that means the position for Roy's ball is negative 4.9 t squared plus 18t. Okay, so what these two equations have got me, I feel like that was bad grammar. What these two equations have earned me is Now I know the position of Sally's ball at time t, and the position of Roy's ball also at time t. So let's check and make sure this makes sense, right? Like, if I put in 0 for my time, then the position is 30. And as the time goes up, the position will decrease because of this negative sign, right? Okay, cool. So when are they going to meet? We need to figure out, what does the question ask? How far below the top of the cliff are they when they cross paths? Ugh, it's a dumb problem. All right, so to solve this, we're going to set these two things equal to each other, right? Because we want to figure out at what time they have the same position. So the position of Sally's ball is equal to the position of Roy's ball when negative 4.9 t squared plus 30 equals negative 4.9 t squared plus 18t. So if I add 4.9 t squared to both sides, I just get 30 equals 18t. Divide both sides by 18, and t turns out to be 1.67 seconds. So that's how long the two balls have been in the air when they cross paths, and then to find the position at which that happens, plug it back into either of these two equations. Okay, and regardless of which one you get, you'll find that the position of Sally's ball and the position of Roy's ball are both about 16.4 meters. Okay, but that's 16.4 meters above the ground, so the distance they fell would be 30 minus that. Maybe I should have made the top of the cliff a position of 0 and made the bottom of the cliff negative 30. Maybe that would have made it easier. But so anyway, 30 minus 16.4 is, what is that, 13.6? 13.6 meters below the cliff. Cool? All right, so now we got to graph these two things. So how do you graph this? So let's go back over here. So let's see. Draw a position time graph that represents the motion of both balls for the entire time they're in the air. Be sure to label your axes. So we need to figure out how long they're in the air for. So let's see. Let's find the time for which Roy's ball is in the air. I don't know why I've decided to start with Roy's ball. I guess because I assumed that it's going to be in the air for more time, maybe, is why I started with that. Oh my gosh, stupid tablet thing. Okay, so let's see. So for Roy's ball, here's what we know. We know that the initial velocity is 18 meters a second. So let's figure out when it gets to the top. So we know the acceleration is negative 9.8 meters per second squared. I cannot talk right now because I'm in the middle of recording a video. Can it wait 3 minutes, please? Cool. All right, so plug those guys in, and we will discover that the time that Roy's ball takes to get to the top of the path is 1.83 seconds, which means that the time that it's in the air total would be double that, or 3.67 seconds. All right. And I guess the other thing we probably need to know is how high it goes at the top, right? So to find the displacement at the top, take your pick of the linear motion equations. I happen to like this one. So when it gets to the top of the path, the VF is 0, the VI was 18, and the time is the 1.83 seconds. So at the top, we're going to be 16.5 meters up. Okay, so that's all the information for Roy. So let me graph that, and then we'll come back and figure out what's going on with Sally. So it looks to me like if I give myself 5 seconds, that should be more than enough time. So, what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, so if I make every 2 boxes a second, then I'm in good shape, right? So here we go. Horizontal axis, time. Oh, you know what? I should do this not color-coded because this will apply to both graphs. So we'll do this in black. So time in seconds. 1, 2, 3, 4, 5. All right, and then my vertical position has to go up to 30. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we'll just number by 3s, I guess. It's a little weird. I don't like numbering by 3s, but seems easy. So position meters, 0, 6, 12, 18. Why am I dumb? 3, 12, 18. Yeah, this will work. 24. Yeah, okay, sorry. 30. All right, so what we know about the red ball is at time 0, its position is 0. We figured out that it was going to be in the air for a total of, come on, stupid thing, there we go, that it was going to be in the air for 3.67 seconds. That's going to be like over here, and that it was going to get to a maximum height after 1.8 seconds of 16.5, which is going to be, I don't know, there-ish, right? Okay, so here's my graph for Roy's ball, all right? So there's Roy. All right. Meanwhile, Sally's ball, I know, is going to start up here at a position of 30, and it's going to hit the ground. I know they cross paths after, what did we decide? When did they cross paths? They cross paths after 1.67 seconds, so hopefully somewhere like right around here. Not quite at the top of the path, but it's pretty close. All right, so let's figure out how long it's going to take for that purple ball to hit the ground. So I'm going to clear up my board over here. All right, so for the purple ball, here's what I know. So for Sally's ball, I know my VI is 0. I know my acceleration is negative 9.8. I know my displacement is negative 30. So I can use this guy to solve for the time. And the time ends up giving you that. Sorry, I'm kind of plowing through the algebra here. And it gives you, did I write it down anywhere on my other thing? I did, 2.47 seconds. So 2.47 seconds is right about here-ish. So it looks like the graph is going to go something like that. All right? So there we go. That is the Sally at the top of the cliff problem.